There we go. Try it again. Can everybody see my slides now? Are they less frozen than they were before? I'm moving them a little bit here.
Yes.
All right, good, good. Okay. Situation averted or crisis averted. Anyhow, the whole thing about handheld models, I've brought them up several times with you already in this class, and it's up to you. You can buy a set for not a whole lot of money, but you know, I went through organic chemistry, and many students do, without having them. You know, you can manipulate things in your mind. But let's go back to that example that I showed you before I started recording this morning. I was showing my students who are here with me. We were looking at two models of molecules that were mirror images, where I had four different spheres connected to a black sphere in the middle, and I said, are these identical? And my students said no. So they knew right away that they are not superimposable, therefore they are non-identical. So this is called 2-butanol, this molecule here. But you can see that the carbon, this carbon here in 2-butanol, is a chiral carbon. It results in a molecule that is non-superimposable upon its mirror image. The reason why is because it says chirality most usually results when the carbon is bonded to 4 unique groups of atoms. I can't stress this enough. Groups, not atoms. 4 unique groups of atoms. Look, you can see that. Let me use the yellow pen. A hydrogen is different than a hydroxyl. A methyl is not a hydrogen, it's not a hydroxyl, and an ethyl isn't a hydroxyl, methyl, or a hydrogen. So those are 4 unique groups. So we say that that is a chiral center or a chiral carbon. Again, if you're having trouble realizing why that's, chiral, again, the handheld models might come in handy, no pun intended. So when an atom, like a carbon, forms a tetrahedral center with 4 different groups, again, groups, we call it a chirality center. Sometimes we call it an asymmetric center. Sometimes we call it a stereo center. There's all kinds of different words that we use for it. I usually use stereo center or chiral center. But anyhow, if we look at all 3 of these carbons that are highlighted in green, each of these carbons is connected to 4 different groups. Let me prove it to you. This one over here, we'll start here. There is a hydrogen going in back here, right? So look, we've got a hydrogen, we've got a chlorine, we've got a methyl group, and we've got an ethyl group. Those, my friends, are 4 different groups. So that carbon that's highlighted in green is a chirality center. Let's go to the next one. We've got a hydrogen going in back here that's not drawn. It's implied because this is a bond line structure. But we've got a hydrogen, we've got a hydroxyl, we've got an ethyl group, and we've got a propyl group. Those, my friends, are 4 different groups. We have another chiral center. What about here? We've got, so let me use a different color pen. I'll use green this time. So we've got a hydrogen in the back. That's different than the bromine. If you look here, this is a methylene, a CH, and this is a CH2. Did I say a methylene when I meant methine? So this is a methine, and this is a methylene. Well, a methylene and a methine are 2 different things, and a bromine and a hydrogen, so therefore that is a chiral center. I have another example I want to show you. What if I was to draw this molecule? Okay, if I put cyclohexane like this, like that, I put my dash like this, and I'll put a chlorine here, okay? My question to you is, would this be a chirality center, the one that I have highlighted in green? Would that carbon be chiral? Would that be a chirality center or a stereo center? Yes or no? Yeah, the answer is no. It is not a chirality center. Why? Because even though it's a cyclic molecule, if we look at it, there's a hydrogen going back here. Okay, so we have the hydrogen, we have the chlorine, but let's go over here. We have a CH2, we have a CH2. We have another CH2. We're going to keep looking until we find a point of difference, and they both meet down here. So the point is this: the pathway going this way and this way are identical. And so this is not a stereo center or a chiral center or a chirality center or an asymmetric center. Okay, it's none of those. All right, there we go. So I think you guys are getting the hang of it, of what a stereo center is. So how many chirality centers are there in each of the following compounds? This is where it starts to get a little trickier, but we've kind of answered the first one already, haven't we? If we call these, if we call this one A, if we call this one B, if we call this one C, and we call this one D over here. We've kind of already answered A, haven't we? Right, because we know that there's a hydrogen going down here, right? So we have the hydroxyl, we have the hydrogen, we have a path going this way, but it's identical to this pathway. So there are 0 chiral centers in this molecule. You can put a big fat goose egg. There's none. Okay, 0 here. Now, I just want to address something that somebody might be thinking of is, you're like, what if you're thinking, well, Mr. Dion, what about all these methylenes, right? What about all these CH2s? Well, those by definition could not be stereocenters because they both have 2 hydrogens that are identical. So whenever you see a CH2 or a CH3, it cannot be a stereocenter, right? Let's move on down. Let's go over here. Let's go over to B, okay? Are there any stereocenters in B? If so, how many? Could anybody identify how many there are? Could anybody identify how many stereocenters? It is not trivial, not easy. Maybe the first time you look at it. Anybody have a hunch? Oops. Yeah, okay. Some people are saying 2. Okay, let's take a look. And this one I don't think is simple. Okay, my students are all correct. I have great students, but I don't think it's an easy question the first time you see it. So let me explain. Because it might be a knee-jerk reaction to say, well, this one's going up and this one's going up. So how do I answer? Well, let's take a look. So the answer is that this carbon and this carbon are both stereocenters. Let me show you why the yellow one is a stereocenter. It's because this carbon is connected to a hydrogen, a hydroxyl, and then look what else. Here we have a CH2, a methylene, but down here you've got a carbon that's attached to a hydrogen, a hydroxyl, okay, and this CH2 over here. So obviously, I mean, 1, 2, these are all different groups, aren't they? So that carbon highlighted in yellow is definitely a stereocenter. Now, if I erase all that spinach, for the exact same reason, the one that I had highlighted in green is a stereocenter as well. It's connected to the hydroxyl, the hydrogen, this group over here, and this methylene over here. Those are 4 different groups, so therefore that is a stereocenter. So we have 2 stereocenters in that molecule. So again, all of my students were correct. Let's move over to C. You know how I don't like trick questions? Well, I don't call C a trick question, but I call it tricky. Could anybody identify how many stereocenters are in this one? I don't think this is an easy question, but it's like anything. Once you learn it, it becomes more abundantly clear. Yeah, that's right. My students have got it. Okay, so there's 2 stereocenters. Let me help you out. It's this one here in green and this one here in yellow. Now, a knee-jerk reaction, I'm going to highlight this one in red because it might be a knee-jerk reaction to say, hey, man, that's a stereocenter because this methyl group is drawn on a wedge, but it's not. Why isn't it? Because this carbon that I have highlighted in red, I'll use my red pen, is connected to a hydrogen, but it's connected to a methyl group and another methyl group here. These 2 groups are identical. So that is not a stereocenter. So we can just delete all that. Okay, that's not a stereocenter. But if I look at the one that's highlighted in green, why did my students know that was a stereocenter? Let me show you. I'll use the green pen. Because there's a hydrogen here. There's a methyl group here. Those are different. I have an isopropyl group here. And I have a sec-butyl group over here. Those are 4 different groups, my friend. So there you go. That carbon highlighted in green is a stereocenter. And again, I know that for some of you, I might be going a little slow, but I want to make sure that we have this down pat before we start cruising at higher speed here. The one in yellow, I'll use the red pen again. I've got a hydrogen going in the back. I've got a methyl group here. I've got an ethyl group here, and I've got all this spinach over here. So those are 4 different groups, and that's why the carbon highlighted in yellow is a stereocenter. And so the answer to this one is 2. Now, if you're annoyed at this question and if you're going, why? Why would they draw it as a wedge like that when it doesn't have to be drawn that way? There are good reasons why chemists do that sometimes. If they're showing a reaction and they just want to maintain some continuity from structure to structure, sometimes chemists will put in wedges where you don't necessarily need one, and we'll probably see that through our travels in the class. Anyhow, we're just looking for chiral carbons here. We'll go over this one a little quicker. There's two of them. There's this one that I'm circling in red and this one I'm circling in blue. The one in red is because there is a hydrogen in the back, right? There's an ethyl group here, there's a methyl group here, and there's all this spinach over here. So that's definitely 4 different groups. The other one, so we'll put a star by this one, which is usually how we denote stereocenters. We put a star by them. This one here in blue, we have a hydrogen coming out here. We've got a methyl group. We've got all this alkene stuff, and then we get this sec-butyl group. So there you go. 2 stereocenters in the molecule. There's no stereocenter here. I mean, these are cis, but we're not looking, those aren't chiral carbons, okay? There's no chiral carbon there. All right. So I think the main take-home message from the last 2 problems, where were they? We looked at this problem, in the last couple of slides, is that it's got to be 4 different groups. I remember the first time I taught this, students would sometimes get hung up on the idea of maybe 4 different atoms. So they would always be looking for 4 different atoms, but remember, it's 4 different groups. Well, I'm really grateful for how well you guys are answering these questions. This, I would say, is a tricky question. The first time you see it, not a trick question, but a tricky question. Could anybody identify how many chiral centers are in this? And I'll give you a second to look at it. I'm going to take a drink of water. Vitamin D3. You know that vitamin D is actually, when we talk about vitamin D, it refers to 2 compounds. It refers to what? Vitamin D2 and vitamin D3. We take in the precursors to vitamin D2 and vitamin D3 from where? We get them from dairy and also from like other kinds of fungi, I guess. But the precursors to vitamin D2 and vitamin D3 are underneath our skin. And then when we go out in the sunlight, they actually react in the sunlight and they get transformed into vitamin D2 and vitamin D3. So we actually don't ingest vitamin D2 and vitamin D3. We ingest the precursors and then the light causes the transformation. Anyhow, a little interesting chemistry for you there. So I don't even know if I could draw the precursor to vitamin D3 offhand, but anyhow, could anybody identify a stereocenter? Well, I think this is not an easy question the first time you see it, but it is in our textbook. It's a practice the skill. So I'll identify one here. This is definitely a chiral center. This carbon here with the hydroxyl group attached to it, right? Because you've got the hydrogen, you've got the hydroxyl. You can see that this pathway going over here is different than this pathway going over here. So those are 4 different groups. The other ones, I have one here, I have one here, I have one here, and I also have one over here. So those are so there's actually 5 in this molecule. So there are 5 or 5. Okay. Anyhow, there's 5 stereocenters there. So I'm just going to leave those with you here and see if you can determine why each one of these is a chiral center. And if you can't, for whatever reason, just bring it back up to me during the next lecture and we'll take a look at them. But those are the only chiral centers. So the one that I have, maybe I should highlight them all. So this one, this one, this one, this one, and this one in my vitamin D3 molecule. There we go. All right, what time is it? So enantiomers. Enantiomers is a word I haven't used yet. I don't think I have. At least I've been trying not to say it because it's just such a, so common in the speech of an organic chemist. Stereoisomers, some of them can be classified as enantiomers. What are enantiomers? Enantiomers are stereoisomers that are non-superimposable mirror images. Okay, so we've got 2 mirror images, just like your 2 hands. They're non-superimposable. That's what the definition of enantiomers are. So only a chiral compound can have an enantiomer, right? You know that this is a chiral compound. Why? Because this carbon is chiral. That carbon is attached to the chlorine, the hydrogen, the ethyl group, and the methyl group. If I asked you to draw the mirror image, could you? Now, probably if I hadn't studied organic chemistry and somebody said, draw the mirror image of this, if you were to reflect that in a mirror, I would start trying to draw it backwards like this. Like put a bond here, then a bond here, then a bond here. So that's going backwards. And then I would put a wedge like this. Then you could even do that. Okay, I'm being silly here. But anyhow, you put the chlorine at the top. And that is the mirror image. And there's nothing wrong with what I've drawn. It is a mirror image. But if you want to draw an enantiomer of a compound that has many stereocenters, trying to draw the reverse of it like this can get pretty annoying, okay? I was going to say daunting, but yeah, I'd say even more annoying than anything trying to do that. So let me tell you, there is a much faster way of doing this, okay, of drawing an enantiomer. And that is every time you see a wedge, okay, you just flip it to a dash. And anytime you see a dash, you flip it to a wedge. So to reiterate, if I wanted to draw the enantiomer of this compound, all I would do is this. Is I would draw the same thing, and I'd take this wedge and I'd flip it to a dash. So just like that. Now, this molecule in red that I'm going to put in the yellow circle is identical to this molecule here. They are the exact same molecule. Okay? If you were to take this molecule, this one right here in the double yellow circle, if you were to stick your hand under that and flip it like a pancake, okay, you would actually end up with this molecule over here. Give me a thumbs up if you just follow me on the idea of drawing the enantiomer just by reversing the bond. And I also want to make sure that you understand the idea that this molecule that I have in the green circle is the same molecule as this one over here in the other green circle. Now, again, this is one of those circumstances where the old handheld models could come in could be really useful. And again, they're not for everybody. Not everybody needs them, but hey, if you need them, by all means, you know, when you're learning a subject, you know, you're learning it. It's not easy when you're learning something brand new. And let's face it, organic chemistry has quite a few concepts. So here's the easier way to do it. This is just a rehashing of what I just showed you. If you want to draw an enantiomer, if I ask you to draw an enantiomer, just flip a dash to a wedge and a wedge to a dash, and there you go. So here we have amphetamine. So if you've ever wondered what the structure of amphetamine is, this is it here. It's not meth. It's not methamphetamine, okay? Meth, like crystal meth would be if you had a methyl group on here. That's methamphetamine. Anyhow, so these are just two enantiomers, right? Because you flip this dash and wedge, and that is obviously a chiral center. But this one here, I mean, this is isopropanol. It says this is not a chiral compound, right? This is not a chiral carbon. Because why? Because I have a methyl group here and I have a methyl group here. So that's not chiral. So inverting the dashes and wedges, just these are identical. So that doesn't really change anything. Okay. I mean, you can do it if you really want to, if it makes you happy, but it doesn't change a whole lot in the world of organic chemistry. So with that in mind, I want to move on to the next section, which deals with designating a stereocenter as R or S.